For a century, steam locomotives seemed unbeatable. 260,000 miles of track and 134 billion ton-miles of American freight riding on their backs. Yet in less than a decade, the EMD 567 didn't just replace steam. It made steam obsolete, rewriting the rules of railroad economics with ruthless efficiency. Reliability targets soared from piston life, measured in mere miles, to 500,000 miles between overhauls. And for the first time, simple maintainability mattered more than raw horsepower. The numbers were impossible to argue with. Less fuel, smaller crews, far fewer breakdowns. This is the brutal truth about industrial disruption, the blueprint that would inspire not just railroads, but entire industries, leaving only one question: why did the unstoppable age of steam crumble so fast when the math changed? At its height, the American steam locomotive was more than just a machine. It was the backbone of a continent's economy, moving mountains of freight and millions of passengers across 260,000 miles of track. Railroads like the Pennsylvania, the Union Pacific, and the Santa Fe built entire empires on steam. In 1929, U.S. railroads moved 134 billion freight ton miles, a number so immense it dwarfed every competing mode of transport. The sheer scale of these operations made steam seem unassailable. Every day, thousands of locomotives thundered from coast to coast, hauling grain, coal, steel, and people through every kind of weather. The numbers were staggering. A single railroad might operate thousands of steam engines, with fleets standardized around proven designs like the 282 Mikado for freight or the 484 Northern for high-speed passenger runs. Each type was tailored for its role, with tractive efforts topping 70,000 pounds and speeds pushing 100 miles per hour on the best main lines. Behind the spectacle, though, was an industry built on constant grinding labor. Steam engines demanded a level of care that bordered on obsession. Water stops every 50 to 100 miles, coal refueling, ash removal, and endless rounds of inspection were the rule. A heavy-use locomotive might require servicing every day or two. Boiler washouts, tube replacements, and firebox repairs were routine, not exceptions. Shops and roundhouses sprawled across the landscape, employing armies of boilermakers, firemen, and machinists. The cost of keeping this vast system moving was measured in time, manpower, and mountains of coal. For railroad management, the economics of steam were both a point of pride and a growing source of anxiety. Operating costs mounted with every mile, fuel, water, and labor ate into thin profit margins. Even as railroads experimented with superheaters and mechanical stokers to stretch performance, the basic equation never changed. Steam was powerful but demanding, spectacular but costly. The entire industry assumed that bigger, faster, and more refined steam was the only path forward. Alternatives like early diesel or gas-electric prototypes were dismissed as unreliable curiosities, fit only for yard work or the occasional branch line. The idea that anything could dethrone steam on America's main lines seemed, to most, almost unthinkable. Richard Dilworth did not just want a better diesel. He wanted a machine that would erase any excuse to stick with steam. In 1934, as chief engineer of EMD, Dilworth laid out a goal that sounded almost impossible at the time: an engine whose pistons could last 400,000 to 500,000 miles before needing replacement. For comparison, the Winton 201A, EMD's previous attempt, barely managed 8,000 miles before an overhaul. The new target was not just ambitious, it was a direct challenge to every assumption about what a railroad locomotive could be. Dilworth's vision hinged on a simple but radical idea: build the engine from the ground up for reliability, not just raw power. Every component had to survive the brutal, non-stop demands of North American freight service. He insisted on a modular design, a system where pistons, liners, injectors, and even cylinder assemblies could be swapped quickly, with parts interchangeable across different versions of the same engine. This was not just about engineering elegance, it was about economics. If a railroad could keep a single set of spares for an entire fleet, maintenance costs would plummet, and downtime would shrink to a fraction of what steam required. The piston life goal became the backbone of the project. Dilworth's team worked obsessively on metallurgy, lubrication, and cooling, chasing numbers that most engineers thought were fantasy. The result was an engine where major components could run 10 to 20 times farther than anything that came before. Some test units even pushed past 1 million miles on original pistons, a figure that rewrote the rulebook for locomotive economics. Dilworth's approach also meant that a railroad could upgrade its fleet without scrapping old units. As new variants of the 567 appeared, the core parts stayed compatible. The same pistons and liners could fit a 567A, 567B, or 567C, letting railroads phase in improvements without massive new investment. This modular mindset did not just lower costs, it gave railroads the confidence to abandon steam, knowing their new diesel fleets would not become obsolete overnight. From the start, every design decision was measured against a single, ruthless standard. Would it keep the engine running, mile after mile, with less labor, less downtime, and fewer surprises than any steam locomotive ever built? The answer, stamped into every 567 that left the LaGrange plant, was yes. Dilworth's reliability mandate did not just kill steam, it made going back unthinkable. The EMD 567 two-stroke architecture was not just a technical choice. It was the foundation for everything that made steam obsolete. At the heart of the engine, each cylinder measured 8.5 inches across and 10 inches deep, totaling 567 cubic inches of displacement per cylinder. This was not a number chosen for show. It was the product of hard calculation, the ideal size for balancing power, durability, and ease of maintenance in relentless freight service. Unlike a four-stroke, which needs 2 full revolutions to complete a power cycle, the 567 two-stroke design fired every time the piston came up. That meant a power stroke with every revolution, delivering immediate torque that matched the stop-and-go rhythm of real railroad work. But the real breakthrough was uniflow scavenging. Instead of relying on poppet valves and a complex camshaft, the 567 used ports cut directly into the cylinder liners. As the piston dropped, fresh air forced in by a roots blower swept through the lower ports, pushing spent exhaust out a single set of upper valves. The result was a one-way flow, clean air in, exhaust out, no mixing, no wasted motion. The roots blower was not an afterthought. It was a cam-driven supercharger, running at twice engine speed, and it guaranteed that every cylinder got a full charge of air at any altitude, under any load. This was more than a detail. It made the 500cc immune to the power losses that plagued steam at high elevations or in heavy weather. The engine's excess air ratio, between 27 and 31%, kept combustion reliable and exhaust temperatures low, key to long piston and liner life. Every element of the two-stroke cycle was chosen for practical reasons. The uniflow ports eliminated the need for complex valve gear, slashing the number of moving parts compared to steam or even four-stroke diesels. The modular cylinder design, with each power assembly bolted in place, meant that a failed piston or liner could be swapped in hours. No boiler to cool, no tubes to pull, no days lost in the shop. The 567's V arrangement, available in 6, 8, 12, or 16 cylinders, allowed railroads to match power to the job, but always with the same basic parts. That meant a single inventory, a single set of tools, and mechanics who could work on any engine in the fleet without retraining. The numbers made the case. With 156 horsepower per cylinder, the 16-cylinder version delivered 1,500 horsepower in a package that was lighter, smaller, and easier to service than any steam locomotive in its class. But the real advantage was not peak power. It was the relentless, predictable output mile after mile, year after year. The two-stroke layout, the uniflow scavenging, and the roots blower combined to create an engine that did not just run, it kept running, with less fuel, less downtime, and less drama than anything steam could offer. This was the brutal truth behind the 567's success. It was engineered for the realities of railroad economics, not nostalgia or tradition. The engine's architecture was a declaration that reliability and serviceability would always beat brute force. And for the first time, the numbers left no room for argument. The real revolution of the EMD 567 wasn't just inside the engine block. It played out on the shop floor and in the railroad yards, where the old rituals of steam vanished almost overnight. Steam engines lived and died by the clock, chained to hours of daily servicing, ash to be dumped, boilers to be washed, tubes to be checked, and water tanks to be filled. Each job took time and a small army of skilled hands. Schedules bent to the needs of the machine, not the other way around. With the 567, that balance flipped. The modular design wasn't an abstract engineering promise, it was a daily, tangible advantage. When a power assembly wore out, mechanics didn't need to tear down the whole engine. They could unbolt a single cylinder and swap in a fresh unit using nothing more than hand tools and a hoist. Swapping a piston and liner took hours, not days. The same went for injectors, cylinder heads, and even entire power packs. The parts fit across different models. So a railroad could stock a single set of spares for dozens, or even hundreds of locomotives. For the first time, maintenance became a scheduled, predictable event, not a crisis. In practice, this meant that a diesel locomotive could roll into a terminal, get refueled, inspected, and sent back out in minutes. There was no need to wait for the fires to cool, no slow crawl to the roundhouse, no days lost to boiler work. Yardmasters could turn trains faster, and dispatchers could build tighter schedules. If a locomotive developed a problem on the road, a service truck could meet it with the right part and have it moving again before the next shift change. The old bottlenecks, coaling towers, water stops, and ash pits became relics. Railroads began to redesign their terminals around the new reality, with streamlined diesel service tracks replacing sprawling steam facilities. The flexibility went beyond just repairs. The same 567-powered locomotive could switch cars in a yard in the morning, haul a freight train over the mountains in the afternoon, and pull a passenger run at night. Road switchers like the GP7 and GP9 blurred the line between yard and mainline power, making it possible to assign locomotives wherever they were needed most. This adaptability slashed the number of idle engines and made better use of every dollar invested in motive power. For the people who kept the trains moving, the change was unmistakable. Steam demanded constant vigilance and endless labor, while diesels asked for planning and a fraction of the hands. Yardmasters, once forced to juggle breakdowns and bottlenecks, found themselves with a machine they could count on. Dispatchers, freed from the tyranny of unpredictable downtime, could move more freight with fewer headaches. The numbers told the story. Diesel terminals cut prep work from hours to minutes, and the time a locomotive spent out of service dropped to levels steam could never reach. This was the brutal truth behind dieselization. The 567 didn't just make railroads faster, it made them ruthlessly efficient. The engine's modularity turned reliability into a weapon, forcing an entire industry to rewrite its schedules, its maintenance practices, and ultimately, its economics. The old ways didn't stand a chance. The math was impossible to argue with, and the clock never ran backward. Railroad finance officers did not need to love diesel. They just had to read the numbers. By 1949, the cost gap between steam and diesel had become a chasm that no amount of tradition could bridge. On a typical Class I railroad, crew expenses for steam locomotives hovered around 6 cents per thousand miles. The EMD 567 slashed that to 2.5 cents per thousand miles, a 60% reduction, achieved not by squeezing wages, but by eliminating entire job categories. The fireman, once essential, was gone. A single diesel could do the work of 3 steam engines with half the crew, and no one had to shovel a pound of coal. Fuel was another blow. Steam engines burned through 3.5 gallons per mile on demanding freight runs. A GP7 powered by the EMD 567 used just 2.3 gallons on the same route, a 30% savings, multiplied across millions of miles each year. Maintenance costs were even more punishing for steam. Where 1,000 miles of steam operation cost 60 cents in repairs, the EMD 567 did it for 15 cents. Modular cylinders and standardized parts meant a failed piston could be swapped in hours, not days. The result? Maintenance expenses dropped by 70%, and railroads no longer needed sprawling shops or armies of skilled trades to keep their fleets moving. Availability told the final story. Steam engines managed 70 to 80% uptime at best, constantly sidelined by boiler work or breakdowns. The diesel ledger showed a relentless 95%. The FT demonstrator racked up over 83,000 miles without a single mechanical failure, and the Southern Pacific replaced 2 484s with a single F7 on a 300-mile freight run, cutting crew costs by 40% and fuel by 30%. The numbers did not just favor diesel. They made the old ways impossible to defend. When the boardroom calculators finished their work, steam's fate was sealed. The era of sentiment was over. The era of mathematics had arrived. In the late 1940s, the battle for the future of American railroading played out not just in boardrooms, but in the pages of trade journals and in the hard numbers of daily operations. Steam loyalists and diesel advocates argued their cases in columns and editorials, but the real contest was measured in procurement orders and train schedules. Railroads watched as the Electro-Motive Division 567, proven on the road and in the shop, delivered on every promise of reliability, serviceability, and cost control. The industry's doubts began to crumble under the weight of undeniable results. The FT demonstrator had already shown that a single diesel consist could do the work of multiple steam engines, running longer between service stops and requiring fewer hands to keep moving. One by one, railroads put these claims to the test on their own main lines. Southern Pacific, for example, replaced 2 heavy 484 steam locomotives on a 300-mile freight run with just one F7 powered by the 567 engine. Crew costs dropped by 40%, fuel use by 30%. Numbers like these did not just win arguments, they changed minds. The tipping point arrived in 1948. That year, Union Pacific announced that all future mainline locomotive orders would be for diesels, citing the overwhelming performance and economic data from their own trials. The press covered the decision with a sense of finality. Railroad Age quoted company officials saying that the era of steam had ended in the West. Other major lines followed, issuing procurement bulletins that made clear there would be no return to steam. The trade press, once a battleground of competing visions, now chronicled a one-way shift. Dieselization was no longer a theory or a trend, it was policy. The old arguments faded and were replaced by a new reality. The numbers had spoken, and the industry never looked back. The EMD 567 didn't just outlast steam, it demolished the entire economic argument for keeping it. Even now, every industry giant from Boeing to General Electric plays by the rules this engine wrote. Reliability wins, support networks matter, and sentiment can't stop a spreadsheet. Industrial disruption is ruthless, and the numbers never flinch. The next revolution will look different, but the math will be just as unforgiving. Share your thoughts below.